Welcome to this video series on systems engineering. My name is Jeanette Stecklein, and I'm a NASA systems engineer. I'm also the lead judge for systems engineering on NASA's robotic mining competition and Lunabotics. We developed this series to describe the key system engineering products and techniques and how to perform them on your project. My team and I developed the rules and rubrics for the system engineering portion of NASA's university level competition. This series focuses on the specific elements we've asked you to discuss in your paper on how your team performs systems engineering on your project. Our instructor for this series is Mark Powell. Let me tell you about it. Mr. Powell performs system engineering to make projects successful across several industries, including aerospace, defense, energy, and commercial. He's taught system engineering since 1989. He's developed and taught 23 graduate courses in systems engineering. He served on the faculty at the University of Idaho, Stevens Institute of Technology, the University of Houston at Clear Lake, and the University of Texas at Austin. He's been with us as a system engineering judge for NASA's robotic mining competition for over 5 years. In 2018, he presented a short course in systems engineering during the competition at Kennedy Space Center. This series is an expansion of that course. Take it away, Mark.
Thank you. This is another in our series of presentations on systems engineering for university-level engineering competitions. Our series consists of 11 different presentations about system engineering. System engineering is a very complex subject. This particular one is going to focus, this presentation is going to focus on the central role of the systems hierarchy, and that's throughout the whole project lifecycle. The objective of this presentation is to refocus, or to focus you, on how important the system hierarchy is in the project lifecycle. The typical hierarchy of a system, you see the levels over there with names. Depending on the project you work, those names may all be different. Typically at the very top, it's system, at the bottom, it's something like parts or components. But this is an example that works with what I've presented so far. It's actually about an air transportation system. And I want to start at the bottom. A part is simply the lowest level of a separately identifiable item, like a bolt to hold a console in place. A component is comprised of multiple parts. You notice we go up to a higher level. This is bottoms up. A cleanly identified item, maybe a cathode ray tube or an earpiece of a pilot's radio headset. We're talking about an air transportation system. A subassembly is an integrated set of components and or parts. You get a well-defined portion of an assembly, which is the higher level. Say a video display, which is going to consist of a cathode ray tube. When this was done, this was in the 70s. And its related integrated circuitry, or a pilot's radio headset. Obviously, the earpiece is part of the radio headset. An assembly is going to be an integrated set of components and or subassemblies that give us a defined part of a subsystem. The pilot's radar console, for example, or the fuel injection assembly of an aircraft propulsion system. The subsystem, it's an integrated set of assemblies, no surprise, components and parts, which gives us a cleanly and clearly separated function. Here's where we're getting into functions. Remember, we talked about functional analysis and functional decomposition. They involve similar technical skills or a separate supplier. Now that range in subsystem and assembly, once we get those described, we're typically really getting really close to where we hand off. Somewhere in subsystem and assembly ranges is where we do our PDR. An element, a major product, service, or facility of the system. You may have a complete facility, an aircraft element of the air transportation. The aircraft itself, these are sometimes called segments. And of course, at the system level, at the very top, an integrated set of elements, segments, and or subsystems that accomplish a defined objective, such as an air transportation system. Now, the key is that we always start at the top-down development. So we start with the system. So we know we're going to have an integrated set of elements, segments, or subsystems that allow us to accomplish a mission, such as an air transportation system. And then we break it down, and eventually it's easier to see on a bottoms up than it is on a top down, but that's the hierarchy actually starts top down. This sounds difficult. It's actually a lot more simple than you think. We've seen this picture before. This is a description kind of these hierarchy elements. Rule of thumb I want to present to you. Each level of that hierarchy should be decomposed to no more than 9 entities. Say 5 is a better number, but 9 is an absolute max for the lower level. Now, you're probably going to be able to identify a whole lot more, but you don't want to decompose more. You have to group things together. And there's a reason for this. And this definitely applies to elements and subsystems, possibly assemblies, possibly subassemblies. The numbers of components and parts usually exceed 9. We're definitely, for components and parts, we're down into the descriptions that are suitable to give to a traditional discipline. So it's appropriate for them to hold. They're used to dealing with a whole lot of things because they're all in the same area. We obviously review this hierarchy at different control gates. The system, which is really at this particular level, we're really describing the problem space completely. We're making sure the problem space is valid, consistent, complete, and coherent. And we review this at a system requirements review. The elements, which is the first breakout that we've got, we review that at something usually called a system design review. These names that are used may be different depending on the program you're working on. The subsystems, usually at a second level system design review, a subsequent system design review, because they're actually starting to get into system design, not the actual engineering design. The assemblies, definitely a preliminary design review. That's where we have these assemblies described well enough in a single discipline such that they could be picked up and actually the formal design done by each traditional discipline with support from the engineering specialties and systems engineering. Of course, the components, parts, and everything, those are the piece parts of those assemblies descriptions that we have given to the traditional disciplines, and they have a critical design review before they actually start cutting sheet metal, before they start building. So that critical design review, systems engineers play a part in that to make sure that the interfaces are there, and obviously the engineering specialties do as well. But that's where the control gates come in with the hierarchy, what we review. Now let's go back to that rule of thumb. The most difficult challenge for systems engineers, never decompose an entity to more than 9 sub-entities between control gates. I say this is the most difficult challenge. A lot of challenges for systems engineers. This is one of the things that's hard for them. And it's a toss-up, really, if this is the second most difficult challenge or if it is maybe the most difficult. But here's how I've ordered it. Never decompose beyond 1 level. Now, typically, if you have more than 9 entities, you typically have multiple levels. So that's the reason why I ordered it. These are hard things. This is the reason why systems engineering requires discipline. The numbers of interfaces possible, the reason why we have that rule of thumb, the numbers of interfaces possible decomposing to 9 entities is large, 36 of each type. Easy to calculate that. The first one is going to have 8 interfaces. The second one's going to have 7. The next one's going to have 6. So it's a sum from 1 to 8 gives you 36. You may have, probably for your system, you're going to have electrical, mechanical, thermal, dimensional, data, software, fluid, operations. I've seen programs where there's 13 or 14 different types of interfaces, and you can have, as say you have 13 and as many as 36. You're getting close to 400 or 500 interfaces you're going to be managing. That's hard to do. And of course, any allocation amongst those interfaces, across those interfaces, has got to add up properly. Add up is a special word. It may not be a simple addition. The complexity that we get with 9 sub-entities is nearly unmanageable because of those interfaces. That's the reason we have that rule of thumb. If you could break it down to fewer than 9 and maybe have more levels, it will go much faster for you. And if you have more than 9 sub-entities, chaos reigns. There's an old management axiom that no person can manage more than 7 people. And I found that to be pretty true. Same applies when you're trying to develop a system. Now, using the hierarchy in system engineering, well, of course, we have top-down design and development on the left leg of the project lifecycle. We use the system engineering process on each control gate with a control gate to baseline before proceeding to develop the next lower level. And of course, the output, which is this new baseline of that process, is the input to start work on the next level, the next decomposition or iteration of system engineering. In bottoms-up integration and verification, well, the system engineering process is used to verify each entity at that level with a control gate, a test review, which is usually real short, not like a system requirements review or a preliminary design review. Test reviews are pretty short. But the point is we stop, we make sure that everything was fine in our verifications before proceeding to integrate that level's entities up to the next higher level entity. And of course, once we're past that test review control gate, the system review process is used to actually do that integration into the next higher level entities with another control gate. We want to stop again and look at how well these things went together. If everything went together as expected, or if we had to do something to make it work before we start to the next, because this new entity that we've just integrated has got to be verified again. So it's a continuous iterative process. In closing, the system hierarchy is truly central to everything we do in the project lifecycle and in systems engineering. I can't tell you how much of a focus it is. Everything you do should be looking at that. It requires a lot of discipline. Remember, discipline is really important. Systems to work only on the current baseline. In other words, not to dip down more levels or to expand too much. Using that 5 to 9 decomposition rule between levels allows us to actually manage to achieve a valid, consistent, complete, and coherent design stage, which is what we want. And of course, we then have a review, a control gate, and a review to make sure that what we believe is perfectly valid, consistent, complete, coherent actually is. Alien eyes will tell us differently. The system hierarchy, believe it or not, no matter how many levels you have, it will allow you to get to a preliminary design review very fast. And that's where the real work that the traditional engineers are going to start doing. Coming up next, the next presentation is going to be on interfaces and integration, which comprise the very largest portion of risk on any project, interfaces and integration. So it's a very, very important. Thank you.